Welcome to Real Physics. This is a series of short clips about unsolved mysteries in physics, and today we are talking about the quantum of action. I will tell you the story in a little different manner, but I start telling it in the conventional manner. You know probably that Max Planck in 1900 discovered, so to speak, this famous quantum of action in his law of thermal radiation, but he was very skeptical about the significance. He said it was an auxiliary quantity, and almost saying that don't take it too serious. It's just a mathematical tinkering I introduced in that equation. It might not have a fundamental meaning, and he was wrong. The one who truly recognized the significance of the now called Planck's quantum of action was Albert Einstein, who in his famous paper in 1905 realized that the energy contained in a light wave was indeed quantized, leading to the famous formula E equals hf, the frequency, and to the concept of light quanta, also known as photons. So then another big revolution occurred when Niels Bohr pondered about the physical units of that strange quantity, and he realized this is an angular momentum. The unit is equal to an angular momentum, and he asked, couldn't it be that this is the angular momentum of of an electron orbiting the nucleus? And it turned out to be right. So we know that angular momentum in atomic physics is quantized, and that led to a big revolution to the explanation of Rydberg's constant and to the, maybe most important breakthrough in the early 20th century of quantum mechanics. And so to speak, the success of this quantum of action continues until modern days. We have Josephson's effect and the quantum Hall effect, also very fundamental and interesting features of nature. But the reason why I'm making this video is because the question that is not asked enough is, why do we need this quantum of action at all? Everybody is happy, okay, that's quantum physics, you have to take into account quantum effects, but we don't know why age exists at all. There has to be a fundamental reason for the very existence of this strange constant of nature, and physicists didn't figure it out yet. So everybody is kind of happy with the concept, and I forgot to mention Heisenberg's famous uncertainty relation, also linking very fundamental properties of nature. And Heisenberg, for instance, says if you go to small scales, you have to apply quantum corrections. But what does that mean? I mean, you have to give a reason for it. And this is also something for mathematicians. I sometimes wonder, mathematicians are very precise and they like to prove everything, and they use, if you talk about laws of physics, we use concepts like differentiability and continuity, and they're happy with this excuse. Okay, if you go to small scales, you just apply that game with quantum corrections and age. So I think instead there has to be a good reason for the very existence of age, and there has to be a mathematical reasons from first principles. By the way, you cannot calculate the number 6.62 times 10 to the minus 34th because it's related to a unit system. It would be senseless to trying to calculate it, as it's senseless to try to calculate the speed of light. But what you need is a qualitative explanation for its appearance, and this must be a consequence of very deep mathematical structures, and physicists have not discovered it yet. That's a big unsolved problem of physics. I hope you enjoyed the video. If you like these kind of fundamental questions, subscribe to this channel.